Hi everybody. First of all, thanks to the organizers for inviting me. It's a pleasure to give a talk here, and also thanks for organizing a beautiful conference. Actually my first real conference in 3 years, and I'm really happy to be here and talk to everyone. I'll talk a little bit about some new results concerning many-body dynamics that we look at with tweezer arrays. Let me start more broadly with the goals that we have in our group. They range from actually building towards quantum computing. We have a strong interest in many-body dynamics, and I'll talk about that. We actually have an interest also in quantum metrology to a certain degree, and maybe to a lower degree we're interested in quantum networks, but maybe a little bit more long-term. What I'll talk about today is some sort of new insights at the interface of many-body dynamics and quantum information, and I'll have both experimental and theoretical results. And you will see this as some sort of also a pretty strong quantum metrology spin in it. Let me jump right into it. So as mentioned, we use optical tweezers and atom-by-atom assembly in our experiments. So let me briefly walk you through that. What is an optical tweezer? It's a tightly focused laser beam where you can trap a single atom in it, and it's already been shown in the early 2000s that this is possible. We use very large-scale tweezer arrays that you can generate either with an acousto-optical deflector or spatial light modulator. In an acousto-optical deflector case, you drive it with a multi-frequency RF tone, and if you cross these deflectors, for example, you can make 2D arrays, and you can make these arrays actually quite large, for example, even going up to 10,000 tweezers if you want to. Now to actually generate defect-free arrays for quantum simulation, you stick these tweezer arrays into a magneto-optical drop, you load them, and then you will have certain defects in them. You image these arrays, identify the defects, and you feedback some sort of into the method that you use to generate these arrays. You can switch off the empty traps and then reshuffle everything into a defect-free array, and this is called atom-by-atom assembly nowadays. You can vary the geometry depending on how much control you have over the array in each given repetition, and can build arrays of some sort of different geometries if you want. So this is by now a more widespread technique, following up on the work initially done when I was at Harvard as a postdoc, and Ante Ann's work in Paris that came out back to back then. So there's a few groups that actually use this nowadays. So the features are you can generate defect-free arrays of, say, hundreds of atoms in 1D, 2D, maybe quasi-3D. The atomic distances are scalable, it's flexible geometries, and it's also much faster than traditional Collier experiment, which will actually matter for some of what I'm showing. There's some limits to it, so you cannot make infinite number of traps, so your laser power limited, and also the total success probability is exponentially suppressed. And basically, if you try to make an array with no defect, the probability to have a defect from a single atom scales to the power of n to actually make it defect-free. So you have to have high fidelities in each of the steps of imaging and transport and so on. Now these are neutral atoms at quite sizable distances, maybe a few micrometers. They don't really strongly interact to introduce interactions. We usually use Rydberg states. This gives you strong dipole-dipole interactions. You could think of photon-mediated interactions too, or you can think of letting atoms tunnel around, and these directions are all pursued in various groups. Actually, Adam is going to talk a little bit more about tunnel physics, he told me. I'll focus mostly about the Rydberg states. So what are kind of Rydberg states and interactions, and how does this play into many-body physics here? Most of you know that, so I'm exciting a ground state atom to a very high-lying quantum number here, and then basically the electronic wave function blows up to pretty large sizes, which leads to a very strong polarizability with respect to electric fields, but also to a strong induced dipole-dipole interactions if you have both atoms in the Rydberg state. And this scales as 1/6 with the distance and has a very strong scaling with the principal quantum numbers. And this leads to very sizable interactions even at these large distances in the arrays, and this is some sort of a fruitful marriage where the interaction is really well suited for the typical atomic distances that I have. Okay, so that's sort of the basic principle. If you think about it on a more many-body level, you can think of global excitation from some ground state to a Rydberg state with a Rabi frequency omega and some detuning. And you can try to map this to a spin model, sigma x and sigma c operators. And now in a rotating frame with rotating wave approximation, you get some sort of single atom terms for each of the atoms with a Rabi frequency and some detuning, spin flip, and some light shift, basically. Then you can include the interactions. The interactions only happen in the excited state. And these interactions they scale with 1/6, and you can tune them quite widely via the spacing in the array and the geometry. That's some sort of the basic idea. So this has been used quite widely nowadays in various quantum science applications. So the first one is really to study many-body physics in a kind of quantum simulation context. The most prominent, I think, is to look at quantum magnetism and phase transitions. There's many nice results on quantum dynamics, and there's also nice results now in topological physics with a slightly different Hamiltonian. And then there's a lot of open ground, I would say. It has also been used in a more quantum computing entangled state generation context. If you look at two qubits and entanglement fidelities, you typically get about 0.97 in alkali atoms, and it depends a bit on also if you try to entangle in this Ground-Rydberg manifold or map it back onto hyperfine levels. Another notable result is to generate GHZ states with relatively high fidelity on up to 20 qubits in these systems. So I think this is a very remarkable experimental progress, but I think we've only seen the tip of the iceberg here, so I think there's a lot more to be done. Let me talk a little bit about limits and challenges. So if you try to do some many-body dynamics in the system, you're trying to implement a Hamiltonian, some initial state and some final state, you will have certain errors in it. First errors come from noise on the Hamiltonian. You can have noise on the Rabi frequency, for example, from intensity noise. You can do tuning noise. From phase noise, you can have positional disorder from atoms not being exactly in the right position in the tweezer, for example, which gives you noise on these interaction terms. To start with, you might have preparation errors. You might not be able to optically pump correctly or prepare the atoms, and you might have readout errors as well in the end. More fundamentally, you will be limited by spontaneous decay eventually. There's typically 100 microseconds, and if you're in an alkali atom, typically if you want to go to an S state, you would go via an intermediate state, and you get a little bit of mixture, giving you additional spontaneous emission. Okay? What we have been working on at Caltech is thinking about, can we improve potentially on some of these limits using alkaline earth atoms, and maybe there are even qualitatively different applications. Okay, so what we set out to do is to use two valence electron atoms, then specifically strontium 88 in our case, and we want to exploit narrow optical transitions and metastable states that are typically used in optical clocks. Now we want to use them in Tweezer arrays. And I should state that we were very inspired by Euterbium quantum gas microscopes that have been before us, and then we actually used a lot of these techniques in these experiments. And also over the past years, a lot of the results that we published were kind of in parallel to results of Adam's group, who will talk next, and also Jeff Thompson's group in Princeton, who have nice results on two valence electron atoms, or alkaline earth-like atoms in Tweezer arrays. So we managed to do that eventually. So in 2018, we had the first paper on imaging single atoms in Tweezer arrays, where we also showed narrow line cooling. For example, the 7 kilohertz transition in strontium we can use to do sideband cooling to pretty cold temperatures directly. We then followed up with a very high fidelity imaging result where we can do imaging with over 4 nines actually. We then showed the Rydberg excitation scheme that I'll explain into more details, and we also demonstrated that you can build a tweezer clock out of this, basically an optical clock, by interrogating this clock transition. And I like this graph a lot because it shows a combination of high-resolution optical spectroscopy at the Hertz level together with single atom readout on the other axis, and that's actually a quite neat combination, I believe. Okay, let me focus a little bit more on the Rydberg work. So how does it work? We start in the absolute ground state, and then coherently transfer atom to the excited clock state, which lives very long compared to the time scale we need for the physics here. So for that reason, we can for a moment forget about the true ground state and work just in this two-qubit or in this two-level system here, where we can go with a single photon excitation to an S-Rydberg state. So there's a few main features. You can go to very large Rabi frequencies. You can have decent power here, and there's a good dipole moment. There's no extra decoherence from intermediate states. The atoms are extremely cold. And we also can employ new detection scheme that follow along the lines of what has been explained before. So we use outer ionization detection of Rydberg states where we can go above 2 nines, and I think it's actually more 3 nines. And in essence, also the Rydberg states are trappable. I think this was a little bit discussed previously, and as Jeff Thompson has actually showed this very nicely. So this is a kind of nice set of features. Now, what about proof of principle? Let's look at single atom Rabi oscillations. To this end, we space the atoms very far apart in the Tweezer array, so they're basically non-interacting, and we drive them with no detuning, and you see basically textbook Rabi oscillation. You can do the same thing over longer time scales. You see up to like 50, 60 oscillations if you do it right, maybe even more if you do echo pulses. At the time, this was the first Rydberg Rabi oscillation with single alkaline earth atoms. We have very high Rabi frequencies. The pi-pulse fidelities are very nice, 99.5 or even higher, without even correcting for preparation and detection errors. What about entangling operations? If you can space these atoms in pairs that are very strongly interacting in the pair, and then the pairs are not interacting with each other, you can think of the following level diagram. You have 4 states, that both atoms are in a ground state, 1 Rydberg excitation, a double Rydberg excitation. If they're far apart, you see these nice Rabi oscillations I showed. If you put them very close together, the Rydberg state gets shifted because of this 1/6 interaction, and then if the shift is stronger than your Rabi broadening, basically you cannot excite that state anymore. That's a famous Rydberg blockade. And if you think about the physics a little bit more carefully, it turns out the Hamiltonian should excite a Rydberg, a superposition state. That's essentially a Bell state, and this excitation frequency should now be square root of 2 enhanced, and we see this nicely in experiment. I'm not showing the square root, but it's exactly a square root of 2, and we see a very high sort of contrast oscillation for going into this manifold. You can do this over longer time scales. You see up to maybe 50, 60 of these oscillations actually, and you can also analyze this in a little bit more detail, and you can see, for example, that the Bell state fidelity that you get is above 99% if you correct for preparation and measurement errors. I think this is a very important building block, really, to go to these high fidelities for applications now in simulation, gates eventually, and potentially also for metrology on top of the clock transition. So that's all good. So what we have been wondering a little bit more recently is, can we really do similar benchmarking in terms of extracting fidelities now on the many-body level? So this is what we call how to benchmark a many-body system. I should say this is an intense collaboration with Soon-Won Choi, who has done a lot of the theory together with us, with his student Daniel Mark. So let me sort of state the problem. So what I want to do is have a similar high-precision type approach to many-body physics. So I want to be able to see if I actually experimentally produce some sort of a target state that I think of. So I try to do some many-body simulation. I target a certain pure state, here with some, time-dependent or maybe time-independent Hamiltonian, and I want to see if I get it in an experiment. However, an experiment typically have some errors, okay, as I mentioned. And in an experiment, typically you would get a mixed state, and that mixed state will be, in a simplified fashion, some classical superposition of the target state that you want to get at and some erroneous state. And so the probability of getting the right state is approximately the fidelity. And that's what we want to get at. So how good are we actually in producing the right target state in many-body dynamics? That's some sort of what we wanted to do. And this is basically just the fidelity overlap, many-body overlap of this mixed state with the target state. Of course, this is maybe on first glance very challenging because you might think you have to reconstruct some sort of the experimental state, and that's just fundamentally not possible for large system sizes. Instead, we use new insights into many-body dynamics to find an efficient estimator for this fidelity. That's some sort of what we want to do. Okay. So let me give a broad overview of how this works. So there's some sort of a target state that you have that's idealized, and that's the experiment. I want to measure the fidelity. The basic idea is that you measure in a single measurement basis, actually. And if you have certain properties of the system right, it turns out some sort of these measurements in a single measurement basis, there's some sort of a good fingerprint of what happens in the dynamics. And if you have a single error, this measurement statistic, that's a probability to find a certain bit string configuration at the output, it actually will be significantly changed, such that if you look at the correlations between these bit strings, it actually gives you a good estimator for the fidelity. Okay, that's some sort of maybe a little bit abstract. But it has been used before, and a good example is the linear cross entropy that is used in Google's actually quantum supremacy experiment, and it's nothing else than a correlator of output statistics if you look very closely. And it turns out, under certain circumstances, this is actually a proxy for the fidelity with pretty high precision, actually. Okay. This has a few nice features. It needs only single basis readout. If the error happens somewhat early enough before the readout, you might miss some errors at the very end. And it requires a number of samples that scales independent with system size. And I find this very, very surprising to date. If you have a very deep circuit and you do these measurements, you only need a constant number of samples to get a certain error bar. Okay. This is all interesting. However, it requires the generation of so-called random state ensembles. And I explained this a little bit more in detail in almost a tutorial way. So we basically need a random circuit to a certain degree, and we need a random distribution of states to actually get some sort of the right fingerprint actually in the system. Okay, so I'll explain what are random states and also how we actually get them in these Rydberg experiments now. Okay, let me walk you through that. So what are random state ensembles? Formally, they're a set of states that are uniformly distributed in the Hilbert space, and you think of many, many states in an infinite state limit. You can think of a programmable device that has some input state and some sort of evolution operator that you can label, and it gives you a set of labeled output states. And for for single qubit system, it's easy to visualize. You have some input state, some unitary that basically some sort of scrambles you on the Bloch sphere. Again, it's a set of pure states. They're not necessarily orthogonal, and they should be kind of homogeneously distributed on the surface of the Bloch sphere. That's a random state ensemble for single qubit. So you could think if this is not just statistical mechanics, why don't I look at just density operators? And there's actually quite important distinction. So what you normally think of a statistical operator, we think of the first moment of a state ensemble. So what I mean with that, I mean that you just sum over these projectors of these states, basically. Okay? Like this is basically average over all these states. Then geometrically for single qubit, it would mean that you just average all of the state vectors and you should end up in the center of the Bloch sphere. It should be basically identity operator, maximally mixed state. Okay? Now you can think of measurements. You can make projective measurements. For example, I can think of the probability to find the state in the up state in a C basis. Okay, so this would be in the chase run of the experiment. You have to run it many times with a given J. I can reconstruct this probability here, and I can think of this as some sort of a fundamental observable I can have in all of the runs. Now this first moment will give you the mean of these observables. I can just sum them up and divide by m, and you can write this as an expectation value of what you would normally think of a statistical operator. Okay, so that's the first observation. However, if you think of fluctuations, so now I want to get like the square, so how fluctuating are my measurement results with the input. These fluctuations are actually not given by the mean, so you actually cannot just look at the statistical operator. It's actually more complicated than that. To actually get the fluctuations, you have to go to higher order. This is like a tensor square. It's a little mathy, but essentially you have to look at the systems in some sort of a double Hilbert space where you have qubits in multiple Hilbert spaces that you sum over in a particular way to construct these second moments of the ensemble themselves, and with this you can actually get all of these variances of these distribution functions. Let me illustrate this a little bit more maybe intuitively. So essentially what I'm saying is I'm trying to describe full counting statistics. That's some sort of the essence of that. So I look at these, say, the probability to be in the up state as a function of some sort of the state that I'm looking at, in the state ensemble, and it will fluctuate quite heavily if this is a random state ensemble. Now the statistical operator gives you the mean value here, but what I want to get at is a higher order, basically histograms. I want to count how often I have this result in a certain bin, and basically construct some sort of a probability distribution for finding certain measurement outcomes. Okay? And I can do that now, say, for d equals 2 system, for the single qubit system, and it turns out for random state ensemble, this is a completely flat distribution. You can think of the Bloch sphere and basically projecting onto one axis, and you have to count correctly, and it will actually be completely flat. And sometimes this fact that this is flat or that this is actually a broad distribution is called anti-concentration. Now what about errors? If you have errors in the system here and you sum up over many errors, think of running it through a many-body open system dynamics, like a master equation. Actually, these states will not be pure anymore, so we'll get mixed states out. So they will be a little bit shorter here, okay? And it turns out if you then look at these counting statistics, there's not enough fluctuations anymore, and it will lead to a much more concentrated or much more peaked distribution, as it's sometimes called concentration. So generally speaking, decoherence leads to peakier distributions in these systems. Let's go to the large D systems or large dimensional Hilbert spaces. I can do the same thing. Now I can look at the probability of finding some bit string combination in the system. Again, I look at counting statistics, and it turns out if it's random, it's actually a so-called Porter-Thomas distribution. It's an exponential distribution. Again, this is called anti-concentration. And then if you have errors, again, you get some sort of a peak distribution, and it's called concentration again. Another kind of buzzword you might have heard is these patterns here. They're sometimes called speckle patterns, so they're many-body speckle pattern, and in a sense, a fingerprint of the dynamics that you're actually doing in the system. If you have an error, you will get a different speckle pattern. If you have many errors, you sum over many different speckle patterns, and they become more flat, and this is why basically this thing becomes peaked. Okay? And some sort of, if you have an error, you can correlate these speckle patterns in a specific way and figure out if you had an error or not. That's some sort of the fundamental thing for these benchmarking ideas. More formally, if you want to benchmark, you can look at the second moment, in this double Hilbert space, and it turns out there's a swap operator in there. And if you do a little bit of many-body physics, you know that swap operators can be used to do measurement, state overlap measurements specifically. And this formula by itself is really at the heart of very many different protocols that are used these days. So it's at the heart of cross-entropy benchmarking that Google is using, heavy output generation tests that actually enter into quantum volume definitions from IBM, randomized measurement toolbox that Peter and Rainer have been using, ion traps, and a few more. It's essentially always the same kind of tricks, basically. Okay? So in essence, if you have something, a randomized state distribution of a random unitaries, you can produce do benchmarking. Okay, the issue here, however, is that it requires some explicit randomization of the dynamics. So what I want to get at is a question which we have been asking for a while is, does many-body dynamics generally or naturally produce these random state ensembles? So it has both some sort of fundamental implications, but also practical ones in terms of benchmarking these systems. Let me walk you through that actually with a preliminary data set that's not published, but it's a little bit easier to understand compared to what we published already. So imagine you have many-body dynamics with a time constant Hamiltonian, you get a time-dependent output state, and I could think of maybe naively, maybe why don't I just sample from different evolution times to generate different states? Okay, so I can basically watch this thing through the Hilbert space, it's a continuous evolution, and just look at it at different, evolution times. And I can ask, so is this temporal ensemble then, a random state ensemble potentially? Okay. So we did this actually in experiment. In experiment, again, we put, measurements on the output, and we measure probabilities to be in certain bit strings. And then we can look at these histograms. So it's a little bit busy. Let me walk you through that. We look at these measurement statistics. We actually divide by the mean, and we have them for many different bit string combinations. I'm only showing 3. There's 2 to the L of those, actually. There's a lot. Okay. And then there's a few data points here. This experimental data here. Then the solid line is an open system dynamics simulation. The dashed line is actually a fully coherent simulation without errors. Okay. So now what I want to do is I want to look at basically the fluctuations in here. So you see this like really spiky in the beginning, and then it dies out. I can look at the fluctuation in some sort of a intermediate time window. In the beginning, there's nothing universal, but here I might see some sort of the right thing. And then I put everything into a histogram of all of the bit strings, and I look over a few different times, and I see something that's really, really nicely prototomous, actually. So we really nicely see this anti-concentration effect that's basically completely coherent. Now, if you look at late times, you already see the fluctuations are a little bit died out. I can do the same thing. And you see that if you have errors in the system, now we really, really nicely see this concentration effect in experiments. Okay? So this is really concentration is an incoherent effect. And again, this is all on a global level in a many-body system. Okay? All right. So prototomos has really been observed here globally in quench dynamics from temporal sampling. But you could ask, okay, if you're a keen observer, are these really random states? And the answer is actually no, because you can expand these states into energy eigenstates. And at best, maybe the phases are random, but these probabilities in which you have in an energy eigenstate, they're actually fixed. Okay, so it cannot be a random state ensemble. At best, it could be something that is a random phase ensemble. So you have random phases here. So if I basically sample times here, I would generate random phases if I'm really in an ergodic system. So phases are random, but probabilities are fixed, and we sometimes call this random phase ensemble. So temporal sampling gives you this random phase ensemble. As a few consequences, you can actually show how this random phase ensemble is connected to a true random ensemble, and then show that actually this still gives you this Porter-Thomas statistics and anti-concentration for generic measurements that are not aligned with the energy eigenbases. If you the energy eigenbases, there are no fluctuations. Right? So you have to be a little bit off-diagonal, but that's true for pretty much any local basis. And it turns out this is extremely general, it's extremely universal. So if you do Rydberg system, mixed field Ising system, XXC models, Hubbard models, and whatnot, anything that's like interacting, even interacting integrable systems will actually show that to a large degree. So it's very universal phenomena, and it's actually quite nice. And at the same time, if you look at the second moment again, carefully, it actually still has the swap operator in it. And the swap operator gives you the possibility to really do benchmarking. Okay? Before moving forward, show you one more thing. You can also look at the Hamiltonian at a fixed time and generate a random ensemble out of a fixed time from a single state. So this can be done via projective measurements. Imagine we do a projective measurement in part of the system, and we basically, it's a filter type measurement. You think of like you have some sort of a many-body system. I only measure part of it, and I basically count what outcomes I have, and I don't do anything else on the other side to start with. I get basically pure states for each outcome that I get in B. It's a little bit unconventional, but it's relatively well defined. So for each measurement outcome in B, I get a new pure state in A, and if your subsystem is only a single qubit, it will kind of point differently on the Bloch sphere depending on what outcome you have. You can now look at this ensemble of states. We call it a projected ensemble at a fixed time, and I can watch it as a function of time. So for fixed time, I have a bunch of these states, and you can see that it starts some sort of aligned and then quickly becomes completely randomized. Okay? And you can show formally and to a certain degree also numerically that this actually is truly random, so there's no restriction on these phases anymore. We've seen this in experiment. You see, for example, this flat distribution for single qubit quite nicely. There's a little bit of decoherence setting in already. If you go to very long times, again, you see very strong decoherence. This ensemble in numerics becomes some sort of shorter Bloch vectors, basically, and you get this kind of more strongly peaked distribution out. So again, we also see this in experiment. There's a lot of different pieces here, but there's a governing principle in that. And this we're working on right now, this governing principle is that ergodic many-body dynamics generally forms a random state ensembles that are maximally good at hiding information, actually. And it turns out with this you can derive all of these things, and that's some sort of very nice. It's a new kind of framework, in a sense, for quantum thermalization and potentially also for quantum statistical mechanics. Okay, let me show the last part, which is how to use them for benchmarking. Now, using this insight, we can cook up an estimator that we think represents basically the fidelity in the experiment. That should work for quench dynamics with ergodic Hamiltonians, and we can also make a model of the experiment that serves as a cross-check. Okay, so we do this now, and here's a proof of principle. What I'm showing is experimental data doing quench dynamics. So the fidelity should decay somewhat exponentially. You get like the longer you take, the worse your fidelity, basically. And I can compare this to the model where I have both the fidelity and the estimator, and everything is very nicely aligned. So that's actually very good. There's a little bit of delay time. This delay time has to do with errors scrambling into the measurement basis. The estimator works for realistic errors. That's some sort of the bottom line, and it was not obvious when we started this whole story. You can ask a few questions now. So how does this actually scale with system size, and maybe when are you even better than the classical algorithm? I want to get to this a little bit. So we now recently performed more large-scale benchmarking. So this is typically exponential decay that you can fit. There's a prefactor here, p naught to the power of n. That's state preparation and measurement error, which is really good in our case. And then there's some sort of a many-body error rate you can extract that scales actually the system size. And the scaling could, in principle, be nonlinear. We actually now extracted these guys up to 60 atoms now. And you see that it's largely linear as far as we can see it. Okay. So you might ask, how did we actually benchmark anything larger than 30 qubits, where you don't even have a reference state anymore to compare against? So for n equals 30 or larger, at late times, there's no exact algorithm anymore. It's just fundamentally not possible. The reason is because the entanglement entropy in the system is too high. This is a very, very high entanglement entropy regime that we work in. However, we can use matrix product states, and they accept up to a certain max time. So the idea is if your entanglement entropy is not too high, you can still efficiently represent the state, and you basically do benchmarking up to a certain maximum time. So you have this accuracy of the matrix product state is basically 1 up to some certain time before it dies out, depending on the bond dimension in the system. And with this, we can do this fidelity estimation up to a certain maximum time and still get these decay rates approximately at least. You can also do so-called split array benchmarking. These are 2 systems of 27 in that case, for example, to mimic a 54 system. And it looks at the fidelity. If you take the product of these fidelities, it's consistent with the 54. That's another cross-check, which is quite nice. Okay? This brings you into a nice framework. And now we can extract fidelities of many-body systems in regimes where there's basically no accurate algorithm anymore. And then you can ask if the finite accuracy of an algorithm is better or worse than the experiment, and this is what we're looking at. It turns out the 1D systems we work at right now, this is not the case. You can still do matrix product states where the accuracy is higher than the experiment, but the accuracy is never 1. That's some sort of the regime. So both of them are inexact. But the numerics, if you do very good numerics on a supercomputer with extremely high bond dimension, a few thousand, actually it's better than the experiment still, that's our understanding. However, in 2D, this will be much harder. So in 2D, we think we actually can take this question mark and put it into an explanation mark. And it would be some sort of a quantum advantage type test. Okay? It's a systematic framework essentially for comparing quantum fidelity to classical accuracy that we're developing. Okay, we have done a few different few different applications. I want to say one. You can also find Hamiltonian parameters this way, so that parameterized target state depends on what you put into the Hamiltonian specifically. That means also the fidelity is maximum when you match the experimental parameters correctly, and with this you can backtrack the parameters in your experiment right out of quench dynamics without even doing Rabi, Ramsey, or whatever you want to do. So you get the Rabi frequency out, you get the delta out, you get even the C6 coefficient out, which is quite nice, and it works even for local parameters. So if you really introduce disorder by hand, you can read them off afterwards. This has been used quite recently actually by Oscar Painter's group, interestingly in a superconducting circuit where they have no other way of finding out some sort of disorder parameters in the system. So I think it's an extremely powerful method actually for reading out parameters. We did a comparison to digital circuits that I'll skip. The outcome is we find equivalent 2-qubit fidelities in the 99 regime basically. And finally, you could ask about what about different target states. I talked just about quench dynamics. It's not the most general type of setting. The idea is you prepare your target state and then apply a quench afterwards. And it turns out on a wide range of circumstances, this actually converges to the right fidelity of the target state preparation. Actually, you can do this for all kinds of states, and it works out basically. Okay. So let me summarize. I've shown you a few results on alkaline earth atoms and tweezers. I've walked you through some of this random state generation business, which is, I think, quite fundamental, and new benchmarking results. Some of them published, some of them unpublished, like this temporal sampling and the large-scale benchmarking. And the outlook is some sort of what we want to get at is really precision quantum simulations where I can exactly tell you what I did. So I have this Hamiltonian, I know all the parameters in the Hamiltonian, I get a target state with a certain fidelity, at least estimated, and then I can compare to classical numerics. And we hope we can enter a quantum advantage regime within the upcoming years there. And I think there's a more foundational aspect within this random state generation that I'm very excited about personally, which can lead to a new foundation, I believe, for quantum thermalization. Here's the team, so many of my team members are here. I want to highlight Adam, who's in the audience, who has taken much of the data that you see, and Pascal is here too, and we're also building a new cesium experiment. And of course, I want to thank all the funding agencies, these expensive experiments, and you need like a lot of money, which I'm thankful for that. And with this, I would like to thank you for your attention.
Thank you, Manuel, for this exciting talk. We are a bit short with time, but there is time for a couple of quick questions. Yes, please.
So I want to go back to the beginning of your talk when you were telling us about all the errors that you might have doing these things. And then you were saying, well, let's see whether we can do better using the two electron atoms.
Yeah.
And there are some features of the two electron atoms that allow you to do some things like detection.
Yeah.
But a lot of the errors that you were talking about aren't going to be any better with the two electron atoms. Errors in Rabi frequencies and detuning and stuff like that. So could you sort of tell us what the key things are that you're gaining by using two electron atoms?
Yeah, that's a very good question. I'm thinking about a lot too. So there are certain things that are in common. So first of all, you need to be cold, and you could get cold either with an alkaline atom or alkaline earth atom, depending on what cooling method you use. For us, it's very easy to get cold. That's maybe one thing. Then there's all the laser noise business, and this is kind of in common. Actually, might be even a little bit worse for our case because we have to work with UV lasers. They're inherently hard to do. But I think one thing that a lot of people underestimate, you actually have to hit the atoms correctly, and that's again independent of alkaline earth or alkaline just here to get all of that stuff right. I think the only fundamental difference in the end is the detection and the two-photon excitation scheme versus one photon. So we just have a single photon that's very clean. In alkali atoms, you have a two-photon excitation scheme, but nowadays, if you pick the right excitation pathway, you can use a lot of power in the second photon, basically, alkali, and then you can go to maybe what we're trying to do in the cesium experiment. We're going to use a 150-watt laser, basically. And then with this, you can adiabatic eliminate that state. So I think it should be gone. And maybe the only difference in the end is really state detection for these many-body systems. Now, if you want to do quantum simulation, it's a whole different, quantum computing, it's a whole different story. You have to think about hyperfine states, there's a kind of nuclear states versus clock states and all that business in there. I think the jury is still out, I would say.
So one of the things that's so great about the detection is you can use this auto-ionization channel.
Yeah.
But the thing is that you've essentially destroyed your atom when you do that. So is that a bad problem, or can you always figure out a way of using an ancilla to do the job, or?
For the many-body systems, maybe not, but it's the same in alkali. If you do many-body with alkali, you also lose it. So that's always kind of inherently destructive. If you do then quantum computing, you anyway map back to a hyperfine state, so it doesn't matter. For quantum simulation, I don't know how to go to super high Rydberg detection fidelity without losing it, frankly. That's, maybe with an ancilla and two species systems and so on, but it makes it a lot more complicated than what we're doing, for sure. Very good question.
Now, Rainer?
Manuel, very nice data.
Thank
you for the talk. I do have one question. You may have said it, but it went too fast.
Maybe.
In the end, when you just quote fidelities with the benchmarking, does that include the spam errors or doesn't it? And how far is this affected by the readout that you have there?
The first part of the question I understood. What was the very last one?
The fidelities that you were quoting, the benchmarking, does that include spam errors or not?
So,
is it with or without spam?
This is with spam errors included in the plots. Everything,
And
so preparation error, and the detection error is a little tricky because the detection error, fundamentally, you cannot include in an overlap fidelity. It's actually dependent on that, so it's a little tricky. So it's included in the estimator.
Yes.
So the estimator will give you some sort of a lower bound, on the true fidelity in that sense.
Thanks.
Yeah. We have time for the last question, please.
Manuel, impressive stuff. I'm here.
Oh, yeah, I'm trying to find
So you raised this this important question of the state fidelity, and then you showed this randomized state method, which is remarkable because it uses only a single basis.
Yeah, right.
And then somehow you seem to be able to use that to get your state fidelity. Yeah. So do you really get the state fidelity with measurements in only a single basis?
Yeah, that's a common question, and yes, you do. And the reason is that typically if an error is orthogonal, and if your measurement is a little bit later, that error will spread basically into any basis. And that's some sort of at the heart of this measurement. If you can think of an error operator, you evolve it, it's like operator scrambling, it goes into any basis, and as soon as this happens, you can measure in any basis. However, there's a caveat. The caveat is if the error happens basically right before readout in a basis that's some sort of orthogonal to your readout, then you don't see it. However, you will see it at a little bit later time. And this is, I mentioned it very briefly, it was a little fast, but if you look at these curves we had, if you look at some sort of the difference on a simulation level between the true fidelity and that fidelity estimator, the fidelity estimator always lags behind a little bit, so there's a finite delay time. And the delay time is a universal effect. I actually didn't have time to explain this. It's a universal delay time that happens in all of these methods actually and hasn't been a little bit unnoticed actually. It happens in the Google experiment as well. It happens in all quantum volume tests because they're all just single measurement basis experiments. So if you want to then translate the estimated fidelity into real fidelity, you have to take this into account. And we kind of did this here automatically by just fitting decay constants. The decay constants are the same, but it's a little bit delayed, and then you can shift the curves back, basically. That's some sort of the idea. But you have to be aware of that. It's indeed a good question. So the bottom line is that after a finite delay time, you will see any error because it will scramble, and this comes through the chaotic dynamics in the system, basically. And it's the same in a random circuit as well. Google does the same thing, for example. But also some errors there go unnoticed if they're not careful, and they're actually not careful about it, it turns out.
Okay, so you have your knowledge about the process entering in your characterization of the state.
That's right, you need to do that. I think that's fundamentally, I don't think there's another way to do it for large systems than that. Fundamentally, I don't know another way to benchmark a system with 60 qubits than doing these randomized schemes. There's just nothing else that scales the same way, unfortunately.
Thanks. Okay, thank you very much. Time is very short. Let's thank Manuel again.
Catch me in the